Hello viewers, welcome to my YouTube channel Physics with Hrishikesh. In today's topic, we will discuss about the stationary waves, the formation of stationary or standing waves. We will discuss the location of nodes and antinodes and the distance between two nodes and antinodes. Watch the video till the end, and if you like, please hit the like button. Let's start.
Today's topic is standing waves or stationary waves. We know the equation of a progressive wave is given by a sine 2 pi by lambda into Vt minus x, where the terms are usual. Now, when two sets of progressive waves of same amplitude, time period, frequency and wavelength traveling with same speed along the same straight line but in opposite direction, that is, one is coming from the negative x-axis and the other is coming from the positive x-axis, if they superimpose, then standing waves or stationary waves are formed. Now we have to derive the equation of the standing waves. Let the equation is given by y equal to y1 plus y2, where y1 and y2 are two sets of progressive waves. y1 is a sine 2 pi by lambda into Vt minus x plus y2 is given by a sine 2 pi by lambda into Vt plus x. Notice that the amplitude of both the progressive waves are equal. The lambda is equal and they are moving with the same speed v, and the time period is also equal, but the difference is here in the sign. One is negative and one is positive, that is, one is coming from the negative x-axis and one is coming from the positive x-axis, and they superimpose to form a stationary waves. Now sine c plus sine d. What is the formula of sine c plus sine d? It is given by 2 sine c plus d by 2 into cos c minus d by 2. Okay, that is 2a sine 2 pi Vt by lambda into cos 2 pi x by lambda. We can write it as 2a cos 2 pi x by lambda into sine 2 pi Vt by lambda, where 2a cos 2 pi x by lambda is the amplitude. It is the amplitude of the stationary wave. Now, the two progressive waves coming from two opposite directions superimpose, that is, the resultant wave will be like this. And the other coming from the opposite side. Okay. These points where the amplitude of the wave is minimum are called nodes. These are the nodes, and these points where the amplitude of the waves are maximum, these points are known as antinodes. Okay, now let us see the positions of nodes and antinodes and the distance between them. We will first discuss about nodes, where the nodes are situated. I have told you the definition that the nodes are those points where the amplitude is minimum, that is, the points where the amplitude is minimum. I have derived the equation of the stationary wave, that is y equal to 2a cos 2 pi x by lambda into sine 2 pi Vt by lambda, where I have told you that this is the amplitude term. For nodes, the amplitude is minimum, that is cos 2 pi x by lambda is 0, and in general we can write it as cos 2n plus 1 into pi by 2, where n equal to 0, 1, 2 and so on. Now if you put n equal to 0, you will get cos pi by 2, which gives you 0. If you put n equal to 1, it gives you cos 3 pi by 2, which also gives you 0, and so on. Now comparing these two sides, we can write 2 pi x by lambda equal to 2n plus 1 into pi by 2. From this we can write the value of x as x equal to 2n plus 1 into lambda by 4. That is, where the nodes are situated, the nodes are situated at, now put n equal to 0, 1, 2 and so on in this equation. If you put n equal to 0, then you will get lambda by 4. If you put n equal to 1 in this equation, you will get 3 lambda by 4. If you put n equal to 2 in this equation, you will get 5 lambda by 4 and so on. What is the distance between two nodal points? The distance between two nodes is given by lambda by 2. Okay, let us discuss about antinodes. Antinodes. I have told you the definition that the points where the amplitude is maximum, the points where the amplitude is maximum. Okay, now for the amplitude to be maximum, we have to write cos 2 pi x by lambda equal to plus minus 1 in general, which is given by cos n pi. Again, the value of n equal to 0, 1, 2 and so on. If you put n equal to 0, you will get cos 0, which gives you plus 1. If you put n equal to 1, this gives you cos pi, which gives you minus 1 and so on. That is plus minus 1 equal to cos n pi in general. Now comparing these two sides, we can write 2 pi x by lambda equal to n pi, which gives us x equal to n lambda by 2. N lambda by 2. Now we have to locate the positions of antinodes. Now put n equal to 0 in this equation, you will get 0. For n equal to 1, we get lambda by 2. For n equal to 2, we get lambda and so on. That is, here also the distance between two antinodes is lambda by 2. One more thing, that the number of antinodes is given by the number of nodes minus 1. The number of antinodes is equal to the number of nodes minus 1. That is, if this is a stationary wave, if you consider this region, that is, here the number of nodes is 2 and the number of antinodes is 1, that is 2 minus 1 equal to 1 for this particular region. Our new point is transverse stationary wave in a stressed string. Suppose I have a stressed string of length L. If I pluck this point and release, it will vibrate in a loop like this, and and sound waves are generated. Suppose in first case, that is the fundamental mode of vibration. Here the string is vibrated in one loop and these points are nodes and the middle point is antinodes. I repeat, the nodes are those points where the amplitude of the wave is minimum and the antinodes are those points where the amplitude of the wave is maximum. The distance between two nodes is given by lambda by 2 and actually the length of the string is L. That is, we can write lambda by 2 equal to L or lambda equal to twice L. But in transverse medium, the velocity of sound is given by V equal to root over of T by M, where T is the tension in the string and M is the mass per unit length. And we know V equal to N lambda, where N is the frequency of vibration and lambda is the wavelength. Then we can write N lambda equal to root over of T by M. Then N equal to 1 by lambda into root over of T by M. But we have derived here that lambda equal to twice L. That is, we can write N equal to 1 by twice L root over of T by M. This is the case of fundamental mode of vibration where the string is vibrated in one loop. Now case 2. This is the case of second mode of vibration. In this case, the string is vibrating in two loops. You can see here the string is vibrating in two loops. The length of the string is as usual L and this point is node, this is node and this is node and the middle point are antinodes. Okay. Now the distance between two node points is lambda by 2. So this distance is also lambda by 2. The total distance is lambda, which is equal to the total length of the string, that is L. Now we know that N equal to 1 by lambda root over of T by M. Then in this case N1 is given by 1 by lambda root under T by M, or N1 equal to 1 by L after putting the value of lambda equal to L. 1 by L root under T by M, multiplying by 2 in both numerator and denominator, we get N1 equal to 2 by 2L root over of T by M, which gives you N1 equal to 2N, since N equal to 1 by 2L root over of T by M. Okay. Now third case, that is the third mode of vibration. In this case, the string is vibrating in 3 loops. Like this. And these points are nodes, antinodes, node, antinode, node, antinode, node. What is the total distance? Lambda by 2, lambda by 2, lambda by 2. That is 3 into lambda by 2. This must be equal to the length of the string, that is L, or we can write here lambda equal to 2 by 3 into L. Now the frequency is given by N2 equal to 1 by lambda root under T by M, or putting the value of lambda we can write 3 by twice L root under T by M, that is 3N, or N2 equal to thrice N. Now in general we can say that if the string is plucked at length L by twice P, if the string is plucked at the length of L by twice P, then it vibrates in P segments. P number of segments, here segments equal to loop. P number of loops, and the pth harmonic is given by Np equal to P by twice L root under T by M. You can notice that when the string is vibrating in two loops, the frequency is given by 2 divided by 2L root under T by M. When the string is vibrating in 3 loops, the frequency is given by N2 equal to 3 by twice L root under T by M. That is N2 equal to 3N. If the string is vibrating in P number of loops, then the frequency will be given by NP equal to P by twice L root under T by M. That is, all even and odd harmonics are present. Okay, now we know the frequency is given by N equal to 1 by twice L root under T by M, where I have mentioned that the T is the tension in the string and M is the mass per unit length. If T and M are constants, then you can write here N proportional to 1 by L or NL equal to constant. Then what will be the nature of the N versus L graph? This must be a rectangular hyperbola, since NL equal to constant. Now, if in this equation L and M are constant, if L and M are constants, then we will find that N is proportional to root T. Then what will be the nature of N square versus T curve? It will be a straight line passing through origin. This graph is something like y equal to mx, where c is absent, that is, it will pass through the origin. Hence, the n square versus t graph will be a straight line passing through origin. Thank you for watching this video. If you like, please hit the like button and subscribe my channel and press the bell icon. Thank you.